All right, if you're Precalc study guide, we're going to talk about all the exponent stuff on study guide. All right, so when you graph the exponential function, please remember this is general form of y is equal to a times b to the x power. A represent the initial value, usually y-intercept, and b represent the base. When you graph anything, always start with the, assuming a is a positive, well, always start with the base, please. Two cases: when base is greater than 1, when base is between 0 and 1. When base is greater than 1, it's going to be exponential growth. So for example, y is equal to 2 to the x power, right? As x gets bigger, it doubles, so it makes sense why it's going big. Or think of it, y is equal to half to the x power. Your base is a half. Every time it halves, so it's going to be exponential decay, like that. Sometimes you might see some sort of a reflection. For example, if the a values are negative, like for example, you have a negative 1 in the front, that means your y value is changing, so it's going to be x reflection. Sometimes you might have a negative in front of the x, although we have not seen any cases like that, and that's going to be the y-axis reflection. Okay, so these are the example of that. Notice that a value is a 3, base is between greater than 1, so exponential growth, no reflection. Base is a 2, so you start with the exponential growth, like this. But then the a value is a negative, so you got to flip it over. That's why it's going to be below the horizontal asymptote right there. Base is a half. You do the exponential decay, and there's no reflection, so that graph is same as that. Base is a half, so you start with the exponential decay like this one. However, a value is a negative, so you got to flip it over. So if you were to flip that graph over to the x-axis, it's going to look like this. Number 1, which is the following is the expression for that. All right, the fact that it is above the horizontal asymptote, I'm going to assume that, a value is going to be positive. So that's going to be this one or this one, right? Only difference between a and c is that a, the base is a 3, and then c, the base is a third. So I'm looking at it. That's the exponential decay. So base must be between 0 and 1. Next example, it's asking you exponential growth or exponential decay, and what's going to be the a sign of the a, and then the b value. Got it. I'm looking at my input value first, the x value. They're all increasing by 1, equal length input interval values. That's very important. Now I'm looking at the outputs. What pattern do you notice? 72 to 24, 24 to 8. For me, it looks like everything is being 1/3. And that number, 1/3, is your base. Right, so y is equal to a times b to the x power. Your base is going to be 1/3 to the x power. So base is going to be 1/3, that one or this one, right? Well, the fact that all my y values are positive, I'm going to say a value is a positive as well. And is it going to be a growth or decay? Well, base is 1/3 and a is a positive. It's going to be the typical exponential decay. 8. Another reason why it's a decay, look at your numbers. Your y value is getting smaller, so it's getting smaller and smaller. Which of the following demonstrate the exponential growth? I'm going to go ahead and sketch all of them. Always start with the base. 2/3, exponential decay. Any reflection? Nope, so there you go. Is it a growth? Nope. Next. Base is a 2, greater than 1, exponential growth. Any reflection? Yes, I do see a reflection. A value is a negative, so you're going to take that and reflect it over the x-axis. The red one is the answer. Is it growth or decay? We don't talk about the growth and decay when a value is a negative, folks. So no. C, base is 3/2. Well, though that's a fraction, be careful that is greater than 1. So it's going to be exponential growth. Any reflection? Nope. So that is that exponential growth? Yes. I don't want to look at the. And actually if you look at the next section, they're the same function. So to save some time, I am going to just copy the graph from the top. I guess this one I do have to graph it now. Exponential decay, which is, exponential decay there, but then a is a negative, so you better reflect it over. There you go. There you go. That's a graph of a d. Okay. All right. Now, second section is asking you two things. First, is the function increasing or function decreasing? Function increasing means literally y value gets bigger as you go to the right. Function decreasing is y value gets smaller. At increasing rate means concave up, decreasing rate means concave down. Alright, let's go. This one, increasing or decreasing, that is decreasing. Concave up or concave down, concave up. So at increasing rate. So this is decreasing at increasing rate right here. What about this one? Your y value is getting smaller, so it is decreasing. And it is concave down, decreasing rate. Next, it is going up. It's increasing and concave up, increasing rate. And that one is increasing and at concave down, decreasing rate. Next, I gotta sketch that. Start with the base, which is 2, 7. That is between 0 and 1, so exponential decay. I don't see any reflections, so you're just gonna use that graph right there. K is decreasing, and it is concave up. Oops. See. Next, I'm looking at the choices, guys. Multiple choice, always start with the choices, 90% of the time. A and B says they're a linear function. C and D says they're exponential function. So that gives me a clue what I'm looking for. So let's look at it. Input is increasing by 1, equal length favorable interval value. Outputs, what kind of pattern do I notice? Half to 2. Maybe I'm multiplying 4, or maybe I'm adding 1.5. I'm not sure. Now look at 2 to 8. Multiply 4. Add 6. Add, oh, big number, 24, or multiply by 4. Really, I'm just noticing that all of the outputs are multiplied by 4s. So what is that? Outputs are proportional over equal length interval value. That is an exponential function. Now I have to pick the correct reasoning. C says because output over the equal length input interval values are proportional. All my outputs, half, 2, 8, 32, 128, proportional? Yes, they are. C. So D is wrong. What is D saying? Because output over the equal length output value changes linear as the input value changes proportionally. So what D is saying, that your X and Y, your output values are adding and your input values are multiplying. Clearly they're the other opposite. So D is wrong. And we've never learned anything like that. But we're going to learn something like that. Number 7. Exponent manipulation. Look at the choices. Well, look at the problem. Has a 3x on the top. None of the choices have 3 in the exponent. That means I want to get rid of that x, that 3. So I'm going to separate that 3x as 4 cubed to the x power. Remember exponent rule. Exponent to exponent is when you multiply. Right? And then what is 4 cubed? 4 times 4 times 4 is 64 to the x power. Let us see. Number 8, look at your exponent, just the x. All of my choices have 2x or x over 2. That means I have to break that 4 down. So how am I going to break it down? 4 isn't that 2 squared? Exponent to exponent, we're going to multiply it. Anything like that you see? Number 9, my question has x minus 2 in the exponent. None of them has x in the exponent. That means I have to separate that. 2 ways. I'm going to show you both ways. Isn't this 4 to the x power times 4 to the negative second power? Right? You're adding, you're multiplying with the same base. That means you're adding exponent. It's like a backward. Well, let's keep going. That's 4 to the x power negative exponent 1 over 4 squared. That is 4 to the x power times 1 over 16, which I see D. Mrs. Major, you say you're going to show other way. Sure. Watch this. When you're subtracting exponent, that means you're dividing, right? So isn't that 4 to the x power divided by 4 squared? 4 to the x power divided by 16. I know some of you are having a hard time looking at that and think, how is that same as this? But do you know divided by 16 is same as multiplying by 1 over 16? So you can separate that. Either way, answer is going to be D. Next one. The decreasing function gives a number of students in a classroom after school ends. A table gives a value after minutes. It models. Okay, which one is the correct? All right, look at the choices. A and B are linear function. C and D are exponential function. Okay, let's see which one is correct. Inputs are equal length input value intervals. Outputs are, I don't know what that is. Oh, I see. Everything is being 1/3 multiplied by 1/3. So I'm going to get rid of A and B because it's not a linear. If it were to be a linear, you should add or subtract the same number, right? And the fact that your base is, well, the proportion is 1/3, your base has to be 1/3. So I'm going to use letter D. Next. Oh, this one is, okay. So, it should be on the same page, but they're not. Go back and forth. So that's your residual plot. I know it got caught up a little bit. I think there's something here, there's something here, and there's something here, something like that. All right, let's go with that. All right, looking at it, do you see a pattern or no? I don't see a pattern. No pattern. So let's write it down. So residual plot has no pattern. What does that mean? That means a model is good model. You want the residual plot to have no pattern. And it says they actually use a linear regression over here. So let's see. Is a linear regression a good one or bad one? It is a good one because there's no clear pattern. Let's see. Next one. The number of okay, so I have to come up with which equation to use. The number of users expected to increase by 21% each month at t is equal to 0, which is initial value. There are 14 millions. Okay, so y is equal to a times b to the x power. Or some of you want to remember it as a y is equal to a times 1 plus r to the t, or a 1 minus r to the t. That's what we learned in Algebra 2. They're all the same thing. It's just a different ways of representing it. Okay, no matter what you're using, your initial value is always going to be 14. So I'm going to use a value for the 14. The fact that it's increasing by 21%, that means, aren't you going to have 121% next month? Right? So you're going to multiply by 1.12 to the t power. I was using this one. 1 plus, you move 2 decimal to the left, 0.21 to the t power. Okay, so this is what I got when t is what? Every month. Month. But the question asks you if t were to measure in years, which of the following is correct? All right, so this is how we did it at Heron. We talk about what is equivalent to what. So this equation we use every month. So after whatever month, after whatever year, I want these to be the same thing. So you tell me. Isn't after 1 year, 12 months, they're the same thing? Right? So here's what I'm going to do. I'm going to take the 12 and put it into over here, t. So y is equal to 14 times 1.12 to the 12 months. Now, after 1 year, I'm going to put 1 in. I'm telling you, these two have to be the same thing. Why? Because whether you're doing it after 12 months or after you're doing it for 1 year, shouldn't that be the same? So what do I have to do to 1 to make it 12? Shouldn't you multiply 12? After, yeah. So which one is the correct one? Letter B. If you remember the problem with it in the notes, 6.5? I should know it. 6.5 or 2.5 or 2.6. Look at notes. We did the problem like that. It was the other way. It was like every year, and we were looking for which expression is for every month. Okay? All right. Is that it? All right, that's for the non-calculated section. Let's do the calculator section after this.